Welcome to the London Probability Seminar. Thank you for coming. So we have two talks. So it's Derek Ryan and Wolfgang Kendall. And the first talk is about 50 minutes. We start now, we'll have a coffee afterwards. And then we coffee here at the end. And then we resume. So yeah, Derek, please.
Okay. Thank you very much for coming. And you may have heard bits of this before, but I'm sure you won't have heard all of it before. I want to tell you a story that's been going on for quite a long time now. And as it goes on more and more, it seems to migrate in its direction somewhat. I think we are seeing much wider applications, and I think we're also beginning to see some substantial generalizations of the basic ideas of rough class through our better understanding of the algebra that's going on. And I'm going to try and hint a little bit of both of those, while trying also to remind you something of the basic ideas. It's joint work with an enormous number of people. The ones I've listed up there are all actively involved in one way or another with the things I'm actually going to talk about in these slides. I want to start off with something very, very simple and fundamental. And that is just how do you extend a function? Why does that matter? Well, often when we're in mathematics, and particularly if we're in areas like stochastic differential equations, the heart of the matter is that you start with say a control problem, an understanding of how a system evolves, but is driven by some nice system, and then you want to take this operation, this map, from a core and extend it to a larger set. This seems very simple and straightforward. It is simple and straightforward if functions are continuous, but often functions are not continuous, and still it can be simple and straightforward. But there's basically a dangerous bend, a very clear understanding at an abstract function analysis level about when you're likely to have trouble and when you're not. And this picture sort of summarises it. What is the value of sine 1 over x at x equals 0? Right? We've clearly got a problem. And the problem is that there are points arbitrarily close to 0 where the function is quite well defined and say has a value near a half. So surely by looking at those points converging to 0, we could conclude the value is a half. But of course there are other points we could take where the value would be minus a half. And so what's going wrong here is that the graph of this function, which is a nice, perfectly reasonable set in the product space, when we close it, it's no longer the graph of a function. So it's not about operators being bounded, being continuous or not continuous. That's not really the issue. We can handle unbounded operators, but there is always a test that you need to think about. And that test is whether or not the graph of the function, which is just a set in a product space, when you close it, that's just a closed set in a product space, is it the graph of a function? Or could it happen that for a given value of x, you get multiple values of y? If it does happen that you get multiple values for y, it's not normally a disaster either. It's just you realise that your state variable for your function wasn't the correct one. Typically, you need to work out which level you really wanted in the y direction, although this particular example probably isn't one of them. I mean, we sort of know that the sine 1 over x doesn't really have a good value at 0. Now I say that because it's surprising how often in more complex contexts people forget this. They start with a relatively nice object, for example smooth paths, They look at a differential equation, which obviously makes sense. They look at the outputs, the behavior. And then that's a function defined on a set of nice objects. They try to extend it to nasty objects, Brownian paths, things like that. In fact, what goes wrong in a lot of these situations isn't so much that it's not continuous. What goes wrong is the graph isn't closed. This is elementary undergraduate function analysis. But let me just give you an example, an interesting example, which to the best of my knowledge is open and illustrates that there are issues in the way we think about the issues. It turns out that in control, understanding that the basic functional is, with the basic obvious topologies, is not closable, was the whole heart of rough path theory, and has had some useful consequences because observing it and fixing it. But just take another simple example. Take vector fields in L2 vector fields. Now, if we have a smooth vector field and another smooth vector field of compact support, there is no problem defining their Lie bracket. Does that operation have a closed graph? I don't think anybody knows. But if it doesn't have a closed graph, it actually means that in L2, in finite energy, you don't have a clue what it means to take the Lie bracket. You don't have a clue what happens if you interchange the orders of things. Because you will find examples that are close where you thought you did know what happened, which give you completely different answers. So, I don't have a movie of this, but maybe I don't know. But what goes wrong in the control? So let's think of a simple control problem, because that's where I'm really interested. So you have some path, some stream of information, and you have some system responding to it. So you're rolling a sphere along the curve. And now you think of that as a function from the input, which is the stream, the financial data, to the output, which is the rotation or your P&L. And you're interested in understanding that function, and you know what it means for smooth paths. Well, what people wanted to do was they would like to say, well, if our path was uniformly close, then it will produce the same sort of answer. And there are two questions here, all right? There's the question of, is it continuous? And the answer is clearly no. But the answer is does it have a closed graph? And the answer is clearly no too. And it's the second one, not the first one, which is actually an important issue. Okay, why does it not have a closed graph? Well, actually, because of things like this. So, if instead of moving along this path, we actually have some high frequency noise, and we're actually doing that, then it's quite easy to construct an example where this converges to that uniformly, the solutions converge to something and the solutions are not the same. You can have an infinitesimal high frequency rotation messing you up. And that is actually, when you stop and think about it, what makes this functional not a closed graph.
So I don't understand something.
Yeah, hang on. I'm going to have to come a bit closer so I can hear. I just want to make sure that I'm following my own. Yeah? Yeah?
I don't understand in the previous slide. So can you show the previous slide?
Yeah.
The definition of the previous slide.
Maybe try too hard. And don't play this one.
exist two convergent sequences or
Sorry?
exist two convergent sequences or every convergent sequences? Exist two convergent sequences or every convergent sequence? Okay. Exist, and we can take gamma equals to 4.
I think you're right. It should say it is not closable if there exists.
Yeah. Okay. But then
different.
So that
Yeah, you're right.
Okay.
Yeah. Thank you for that. Whoops. So what I want to talk about is the fact that we actually really understand how to put topologies on this control problem, this interaction between evolving systems that allow for roughness. They don't cope with uniform norms, but allow for roughness, and effectively extend our notion of calculus to deal with the interactions of highly oscillatory data streams. It's has been for me a very interesting roller coaster ride because it involves so many different areas of mathematics. It touches really quite intimately with at least the 5 areas I put up there, but I would like now almost to add in a 6th, because I think more and more it's also getting down into combinatorial lockdown algorithms. The analysis of Young, absolutely, Young understood how to integrate paths of P variation against Q variation, where P and Q basically keep below 2, or where P stays below 2. Rounding paths are just outside. He tried very hard to go the rounding path and did not succeed. Chen, exactly the opposite. No analyst, but a geometer. Understood very much how to do nonlinear things. Was very interested in a way in understanding the polynomials on path space. And if you want to understand nonlinearity, then polynomials are a good place to start. Somehow paths represent a free algebra. You can't get much more non-commutative than path segments, and you can concatenate them. There's obviously an operation there. And to do it properly and to do the analysis and the algebra together, you need free algebra. And that's probably well described for the first time in Bourbaki. Or at least I don't know the first time, it's a good source. It needs very much the understanding of Lipschitz functions. We'll come back to that probably a little bit later. And funnily enough, and I don't really understand why, we'll see later on there's a good way of describing paths called the signature. And this is a mathematical object, and there's a relatively deep result by Ben Hambley and myself, and a more recent result by Horatio and Zigeng and the younger people in our community, showing that the signature exactly represents what's going on in the path as a control. And it's a one-to-one map, like inverting a Fourier series. And the interesting thing is, in every one of those proofs, there's some genuine bits of hardcore set theory, measure theory turns up when you really rigorously prove them. I'm not saying it needs the actual choice or anything, but it just needs a result like the fact that a Borel function is a continuous function of a set of small measure. Always needs something like that. There's never been a proof of any of those results that doesn't actually need something like that. Right. We'll try and give you some explanations of some of these. I won't be dealing with number 3, which would surely involve at least a couple of lectures in its own right. But I will, in a sense, emphasize Taylor's theorem. And Taylor's theorem is the idea that monomials are a good basis for smooth functions, or more accurately, that smooth functions are the functions that can be well approximated by linear combinations of monomials. absolutely the basic ideas that you'll see today in rough part theory are that we want to understand objects by slightly unstable. No, that's it, right there. Whatever you're doing. We want to understand objects that are complicated, and the way we understand things that are complicated is by looking at them through certain functions. We look at how they respond, how certain nonlinear systems respond to them. And this is very, very much the idea of Martin's stuff. It's very, very much the idea of Taylor's theorem, really, if you can step back to what one might have understood about smooth functions years ago. Okay. So, I think probabilists have grown up with a rather narrow vision of what is a path. Paths are simply sequential data. Sometimes we put a timescale into them, but actually paths are hugely varied in their nature and their type, and there's loads and loads of them. Actually, this is really the mathematics of stream data. This genuinely is a path, but I built it in the most peculiar way. I took a paragraph of, I guess it was Pascal, I think Pascal. Anyway, it's the quote about order mattering. And I took each character, which if you think about it is represented in the simplest form by an integer between 0 and 255. That's 8 bits. So I took 4 bits and 4 bits, and 4 bits I can think of as representing the motion in, and I replaced the path by literally just the movements given by the bits of letters. And it's a perfectly good representation of that paragraph of text. Okay? So a path is nothing but a path. Alright? You may not want to think of it like that. You may think of better ways to think about it. If you're reading it, there probably are. But nonetheless, it is a path. It's the sort of thing that probably should feel comfortable with and be able to study. And one of the interesting questions that children should certainly learn to deal with, but we're maybe not so good at as mathematicians, is how would you summarize a text? How would you précis a text? What is a good way of summarizing it so as to capture in the broadest sense its effects? And that's very much a good question in the context of rough paths. If I give you a complex path, is there a rational, a good way of giving a rough summary of it over an interval? And this fundamentally differentiates the way of thinking about data from rough path theory from the classical approaches of time series. The classical approach of time series is very much a Kolmogorov vision, that you look at certain times and you try and say where something is. Actually, the rough path vision is almost orthogonal. You can prove by taking the value now through the path you've got and so on that you can obviously get them together. But the rough path vision is that you have a partition of time and you try to give some sort of summary of what's going on over each interval. It doesn't have to be perfect any more than the other description was perfect, but it has to behave in a reasonable way that if we take the summary over 2 halves of this interval, we should be able to put them together to get a summary over the bigger interval, and it should be consistent and it should be improving as we sample and so on. And it's a fundamentally different way of managing the information. But if we take an open-minded perspective and go back to thinking about books and things like that as paths, we realise that this is what human beings do all the time. Nobody would think that a good summary of a Shakespeare play is to give you the 17th word, the 93rd word, and so on, and give you the values at certain times. This is not a good summary. You could do, for the same amount of information, you could give so much better summary by saying, Falstaff made a joke, or whatever. It's just, you would not do it by sampling it and giving the value. However, you can get very confused because obviously if you sample frequently enough, you have the full information. If I know every word, then clearly I have enough. So what happens is you have this very bad description that suddenly becomes good at the end, compared with something which is basically a good description from the beginning. And this, when you think about it, is why the analysis is so much more effective. So data comes in a number of different forms. This is a market data. I put it up largely because I quite like the slide. But it emphasises the fact that you have very many different things coming in. So this is the order book effectively. You have bids, you have offers, you have actual purchases, and those represent the three lines there. I don't want to go into detail, I'm just really trying to tell you that data streams come in many different forms, but the map to handle them doesn't have to. But it does have to cope with the fact that there is no reason generally why the different streams should be the same type. We did some quite interesting analysis trying to understand and predict changes in mood from information which was returned by weekly questionnaires. And the weekly questionnaires give some vector of scores. And that's fine, but actually not everybody filled in the questionnaire every week. And not filling it in, I think traditionally one might be tempted to try and guess and interpolate, but much, much better to think of it as another piece of data. It's simply, but the timestamp sometimes gives you a score, the timestamp sometimes gives you no score, and that's a move in another dimension. Streams of data aren't necessarily numerical, they aren't necessarily low dimensional, but they get very painful if lots of them change at once. So typically they're locally sparse, or at least the ones we can handle. So I like to unify this because I want to do math, I don't want to waffle all the time. And the way I try to unify it, which with hindsight now is not quite right, because there are things called branch rough paths and so on which reflect what you'd have if you had a control or if you're doing numerical. But anyway, I like to model these in terms of their interaction with other systems. There are different ways to interact with other systems. If I give you a collection of vector fields F, I can write down a differential equation like this, I can solve it, and I can understand gamma by asking that I know enough about it to be able to predict the different Y's that will come from looking at different F's. It turns out that in PDE contexts and higher dimensional contexts, sometimes you really need to pay attention to facts a bit like Ito, that the things that you can actually do with your data are limited in some respect. That's where branch rough paths come in and things which if you've ever seen, but I'm not going to go into those today. So there are natural ways to go further, and this is where the algebra starts to get complicated too, because you start to have not just tensor algebras, but other algebras. And something rather magic happens if you take this model, particularly if you take a linear equation, which is simple, because you can just do Picard iteration. If you do Picard iteration, you end up writing down your solution as a sum of the approximations plus a remainder term, and the remainder term in a nice example absolutely goes to 0. So you end up representing your solution in what I think is a sort of magic way. And why do I think it's magic? Well, because I think when you're trying to understand something, what you look for particularly is a separation of ideas. And here we have a separation between A, which describes our system that we're looking at, and these objects, which if you ever write them down are really horrible. The first few times I wrote them down, you could see people's faces graying over as you wrote down these iterated integrals. Now they sort of understood them as a symbol, they could think of it as one block, but you've broken it up into two absolutely clearly distinct parts. One part is purely a description of a part, and the other is purely about the system. And that's actually really, I think, quite magic, because it's saying there's a whole load of things we should know about our part, that will tell us what will happen in any system. It gives us a way of separating out what we need to know about our stream of information that allows us to be mathematicians rather than engineers in a way, because we don't have to say, oh my God, we can't do anything until we really understand how we're going to use it. It gives us a whole agenda of things we can think about before we go out into the real world and see, well, we didn't really need to know this bit, and so on. So it says, okay, great. This bit, by the way, well, we'll talk about it. So it says, great, there's a system here, but really and truly I should understand these objects on the right. They are a way of describing the past. They're not nice things, because our stream is typically moderately high dimensional, maybe two-dimensional. And so when you product things that are two-dimensional, you don't have a product, then they become 4, 8. This dimension of these objects grows exponentially. They're not nice. But they are a description of the path, of the inputs. The good news is actually we're integrating over a simplex. A simplex is inside a cube. But when you think about it, there are n factorial distinct simplexes inside a cube. So the volume is like 1 over n factorial times the bit length to the n. And factorials beat exponentials any day, but not for a while. So what typically happens is the first few terms really matter, but then suddenly this thinks that the factorial kicks in over here and completely destroys the exponential growth there, and you very quickly see that you get some exponential growth for a while, all the terms matter for a while, and that's a very sharp horizon, and after that, nothing matters at all. You can predict the effect of y from these terms, from the first few of these terms. And that's exciting, because that's actually saying that the stream of information can be well summarized by this finite number of terms, even though this is a large thing. It no longer matters how frequently the data came in and things like that. Suddenly, we found this way of giving a global finite description of what's going on that allows us to predict. So, for example, it will allow us to look at the tick data on a market, summarize it into a few hundred coefficients that would then allow us to see what would happen to any hedging strategy. So if I wanted to know how much X should have made and how much Y should have made and how much Z should have made with their different strategies, I will have collected this amount of information and I can put it together. So the point is that this Picard iteration has isolated a very fundamental object that describes our path, our stream, over a time. Remember, the goal is not to describe it at a particular point, it's to give a broad, rough description over an interval of time. Where does it live? So far I just said that the nth term is exponential. Well, if you think about it, it lives in quite a big space, but it's a space we can understand, particularly if our vector space was finite dimensional. If our vector space was finite dimensional, we can think of it as being spanned by a finite alphabet of letters. If we think of it as being spanned by a finite alphabet, then we can think of the nth iterated integral as being linear combinations of words of length n. So we can see that the whole collection of iterated integrals is really a weighted combination of words in this alphabet. Now words, funnily enough, are things you can multiply, at least from a mathematician's point of view. Because you can take one word, and you can take another word, you can put them together and you get a longer word. So actually this space spanned by the words, and the empty word as one, is actually an algebra. You can multiply things together. And when you sit down and think that through and go back to what that complicated sum of iterated integral, you've made a massive change because you no longer need to write down any integral signs or anything like that. You just write down that non-commutative version of the exponential function, and you discover that is what those iterated integrals are. So this is a bit of geometry, if you like, that the iterated integrals thought of as a sequence are really just the equivalent to the exponential function, but for parts. And you could write down the differential equation they solve simply as ds is s times d gamma, where the times is the times in this space of words. It's easy to see from this two important things. One of them is that it's closed under multiplication. Because if I take two pieces of path, it's a little exercise, but not a hard one, to see that the signature associated with the first piece of path and the signature associated with the second piece of path, so you solve this one. If I multiply them together in this algebra, I get the signature associated with the concatenation. Concatenation is a homomorphism from these path segments into the tensor algebra. It's also, so it's closed under multiplication. It's also got inverses, because if I have a path, I can run down it backwards. And it's very easy to see. If I go along a path and then backwards, I actually get to where I started. So actually the range of this map is closed under multiplication. It's got inverses, it's inside of an associative algebra, it's a group. So this is actually a representation of the monoid of path segments with concatenation into the group-like elements in the tensor algebra. And it gives you a completely new way of thinking about this stream of data. That you can think of it as being roughly described by those first few terms in the signature. But it also gives you something else. For those of you who know something about tensor algebras, you'll know that this is actually a Hopf algebra, and you will know that the group-like elements actually have an important role to play, because it's actually the Hopf algebra is generated by this group effectively. But you'll also know that the dual object is interesting. And this is something I want to focus on a little bit, because it's actually very important. This is Taylor's theorem. So, at the moment, if I can put it crudely, we stop thinking about our paths as paths, and we've replaced this description by some sort of series of algebraic coefficients. We've represented our paths as points on a curve, this curve of group-like elements, this group, living inside this linear space spanned by the words. So your typical path at some point here somewhere. I'm very interested in understanding the functions on path space. And this is what Chenery understood again, the polynomials on path space. We've seen some polynomials on path space. Those iterated integrals are multilinear functions on paths. Stick in a path, do the computation, you get some tensors, look at the coefficient of a given word, and you get a number. So you have real value functions corresponding to all those iterated integrals. What you did, or what I did in that sentence, was to identify the dual space of the word, the space bound by the words, as coordinate iterated integrals. Every point in this linear space, which is the dual of this one, is a coordinate iterated integral of this path. So it's a real value function on path space. That's sort of obvious, right? Because it's a linear function on the whole linear space, and I can restrict it to what goes on this curve. What's surprising, even magic, but completely standard if you really understand Hopf algebra, is there's a product structure over here and a abelian product structure over here, because this is a co-abelian thing over here. And what that really says is, if I take two of these points, two of these linear functions, and view them as real value functions over here, then this group is the group of characters in this algebra. What happens is if I multiply these two together, I get another real value function. But it would surely look like a quadratic function. It's a multiple of two linear functions. But the miracle is that this quadratic function can be rewritten as a sum of linear functions. Not everywhere, of course. Outside here it's quadratic, but on this curve it can be rewritten as linear. Now why does that matter? It matters because it says that if I take two iterated integrals and I think of them as functions on my path, two things like this, and I multiply them together, I get a sum of them. And that means that this space of functions is a rich space of functions. It means it's an algebra. It contains the constants. You can see it separates points. So actually, by applying your undergraduate Stone-Weierstrass theorem, you would realize now that all of a sudden you have a class of functions, these iterated integrals, which look like polynomials in a very rich way. They're rich enough to actually describe in a uniform sense all functions on paths, all continuous functions on path space on compact sets. So they're very much like polynomials. And this is an extraordinarily powerful thing. And it comes from the algebra, and the algebra tells you how to do it in some other situations I'm not going to talk about. But it gives you graded family of monomials. The other important thing is there's only finitely many of any given degree. This problem is about describing functions on path space, so that's a big space, but what it gives you is a graded family of functions that is rich enough to get every function, but we start with a few functions and more and more and more until you have a rich enough combination to get at the function you want. So I would draw your attention to something like neural nets. The main theorem which justified neural nets originally was just such a function then, that the linear combinations of them were rich enough to approximate any continuous function. It's also interesting because it says if I take polynomials in these objects, I can rewrite them as linear things. So this actually makes a powerful case for doing things as simple as linear regression. And we'll see that later on. Well, I'm sure I'm slowly running out of time. Or maybe quickly running out of time. So, very quickly, I want to tell you about some of the more recent stuff. So, the way things have worked, we started off by looking at tensor algebra. We moved to that quite slowly, really. And many people still don't. You'll find many of the books in the subject deliberately stop when p gets to 3, and this is, well, when p gets to 3, yeah. And this is really because they don't want to do the algebra. If you want to go beyond 3, you really have to start introducing algebraic objects. But I think I can explain a little bit how the algebra is maturing in the next slide. And it's actually, I think, very important. So, there's a recent paper by Daniel Yang and myself where we explain that looking at everything from this perspective, you are able to integrate and solve differential equations, not just driven by smooth paths, but driven by quite aggressively oscillatory paths. That was in the original rough-path theory. But what wasn't in the original rough-path theory is the kind of objects you could integrate. Originally, I made a big compromise to integrate nasty paths. And the big compromise I made was my one forms would only be on the space, they wouldn't vary with time. But now we really understand how to do the variation in time as well as with space. And the trick, actually, is that when you look at your path downstairs, you can lift it upstairs, whatever that means. But as you lift it upstairs, you turn polynomial one forms into polynomial functions. And anybody can integrate to to turn what looked like a complicated integral of your part into simply the integral of an exact one form upstairs when you've lifted your part and given the extra ingredients in the area or whatever, this dealing with the lack of closeness of your operator. And then everything looked nice, and then you use Young in a simple way to vary over time. I don't want to get too involved in it, but one of the things that comes out of this, though, is that it's an infinite dimensional theory. There's nothing finite about it. It works for Banach spaces. You don't write down alphabets in the end, because alphabets would limit you. And one of the things that's a bit strange is to actually identify the models it does work for, because it's proof by case in a way. And one of the interesting things that's happened recently is that Dan Yu has recognised that, in fact, there is a way of doing this analysis without any particular vector space. And it turns out that to do it properly, there is a natural object, which is what's known as a permutation algebra, which is sort of the object you look at before you put in a vector space V. And that's sort of really quite interesting, because it applies to the branch rough paths, it applies to this case, and it's sort of not so intuitively interesting, but it's certainly theoretically interesting, because it gives a sort of universal way of proving these things. I don't want to go into detail about it. I want to go back to the practicalities. And the practicalities are that because these integrated integrals are factorially fast, and because those estimates are uniform and quantifiable, we can actually really well understand what happens when we look at one of these functionals called solving an SDE. And moreover, we are really doing something quite slick. We are saying that the response is a linear combination in a precise way of these iterated integrals. Because polynomials can be rewritten as linear things, we end up with this conclusion that almost any function we want to look at least locally, can be rewritten as a linear combination. This is the same idea as analytic functions. It's the same idea as polynomials. That you have a basic collection of objects, and that the objects you're interested in can always be written down as linear combinations of them. It's not true globally, but it can be very powerful locally. And this actually immediately allows one to get much more practical, because you don't need a theory and you don't need statistics to put a straight line through a load of points that lie on a straight line. If your function is well approximated by a linear combination, it's not normally a really challenging job to find out what the linear combination is. You know, you can do least squares, and it doesn't even matter what norm it is, because it's not that they're different when you're playing an approximation. You're actually finding a line that goes through. And here is a very simple example of a problem we initially looked at by Tessie, but she looked at a different question of whether you get the equation back. I want to persuade you that actually who needs stochastic differential equations half the time? Because actually you can learn what the stochastic differential equations are doing without any theory anyway. And so what Nihal did, or Hal Ni did, is that she simply generated a sample of x's and looked at the response. And we kept half of them back as a training, as a back testing set, and used the other half to fit your straight line. And we do more or less the obvious thing, and here is the result. So it's a perfectly reasonable ordinary SDE, and we simply try to write the output as a linear combination of the signatures of the inputs. And we have two sets. One set is for training, and the other is to see whether we've overfitted or screwed up, because you find your linear combination that works, and then you apply it to predict what your SDE is going to do to the next piece of the noise. And here is the example. So the top one is the training, and of course we can match the data, and there's the residuals on the left-hand side. But then we do the testing set completely dependent, and you see you get more or less the same answer. And you never needed the SDE to do that. Nor did you need to model the kind of noise that you had. And now I want to say, well, actually, that's a very simple case of machine learning. It's a very simple case of trying to understand functional relationships from data. And I think probably there are more things than we care to admit where we should use machine learning to determine functional relationships rather than waste years and years trying to think of the correct form. Clearly, there are going to be some times when you should determine the correct form, but there are times when you just want to know the answer. And the key idea is that you want to determine a function from data. And one approach to doing that is to try and find a basis of functions, and to try and write your functions as linear combinations of basis elements. Because obviously, as I said before, if it is a linear combination, and if you have enough data, it shouldn't be too difficult to find out which linear combination. This really is just putting a ruler through 11 points. So what do you need for that to work? Well, first of all, you need your basis of functions. And secondly, you need exactly a result like I was talking about the shuffle products and the algebra structure. You need to know that your functions are rich enough that any polynomial function can be rewritten as a linear function. You need to be able to rewrite your functions as linear functions in this basis. But you know you can. You know the signature is a rich enough thing to do that. So then often what you're faced with is, you're faced with some class of functions that does parts that does A, class of parts that does B. So what you're really trying to do, if you have given another path and you have to decide which of the two it is you're really trying to learn the function as this 1 on one set and 0 on the other set, so that you can evaluate it as a new one. The other thing you need to do, so my English got broken a little bit there, is you need to know that the functions you're looking at are rich enough to capture all the paths. You can't have paths that cannot be discriminated between or distinguished by your functions. So they need to be in algebra, they need to contain the constants, but they also need to separate the points. Separating the points is a relatively deep piece of theory. You'll find the paper that does it for rough paths is quite remarkable. We tried for many years to do it before Horatio became that newfound solution. And there's actually an advances in maths last year. But it can be done, so it's separate. So it really is a good class to do these things. So the first case we did of this, I don't know, how long are we doing for time?
5 minutes, I think.
5 minutes left, right? So the first case we did of this was actually simply to look at market data over different half-hour periods and see if we could tell the difference. Once you've normalised out all the obvious things that should let you tell the difference, like volume and things like that. And we discovered that in general you can't, because we'd correctly normalised everything out. But there were a couple where you really could, and by using lasso and so on we were able to. So this is literally just trying to find linear combinations of the functions 1 on one set and 0 on the other. Because we know that these things are broadly speaking the smooth functions, the polynomials, it does make sense because we're trying to keep the low order terms and so on. Anyway, so you may have seen this before, so I won't take too long over it. You actually get some very nice results. And the nice results, I think, would be because these are the times of day where you get open outcry. On one side, again, is the training set. On one side is the testing set. And that's the ROC curve. And you can see actually that these projections using the signature, as they should, provide nice visualizations of the data. But we've moved on since that, and I think you may well have seen them. And I was hoping that this slide in between here could be a video, but we didn't manage to make it work. So I thought I'd finish with what my title promised. And it doesn't matter much. One of them is for the Android and one is for the iPhone. Except the iPhone. And what these are is little marketing adverts for a product. The product is free, but the product actually is that you or some actually I think typically your parents, because young people aren't very good at writing in Chinese because they use pinyin, want to write symbols on their phone and send the email as a result of it. So this actually is a path. It's a path that has strokes and then a movement of the paper and then another stroke and so on. And there is a technique called deep learning, which is pretty good at looking at images and learning from them and classifying them. In fact, it's remarkably good in practice, but it's not perfect. And Ben Graham in Warwick had the interesting idea of refining that by adding in an extra set of features that came from understanding the signature of these paths and the low-order terms in the signature. And it turns out that feeding the two together got Ben to win the worldwide competition for doing these things. Beat McCunn people, but then colleagues who we now collaborate with in South China University of Technology engineered this properly and went back and studied it, what really is your resource, and it basically beats everything else. And it's been downloaded at least, the stats on the website for the Android would say between 1 and 5 million times, and on the, I don't know really the stats for the iPhone, but I suspect it's similar. I do know that the Android calls home, and they've translated well over 4.5 billion characters. I don't know what the iPhone one is, because they don't call home. But the result is that it clearly works. And it does better than other things. But it also is a generic technology. And in the last few months, with colleagues from South China University of Technology, from France, Germany, and with some suggestions of data sets from colleagues in the US, we've been trying to use the same methodology to understand actions. And if you take a movie, then you'll find that there are some well-publicized data sets where they take 1,000 different clips of YouTube, and for each of these 1,000 clips they have one of 21 actions. I guess they start with the actions and then found the movies, and they annotated the locations of what they call landmarks on the body. They fit templates and work out where they are. And then what you get is like a 2-second or 1-second motion of this image. And you need to classify it into which of the 21 different actions are there. Now, interestingly, this methodology works really well because your body becomes a stroke, or several strokes. The signatures of those strokes then become strokes in time. And putting that all together in a pretty natural way, we again achieve, I think, 82% accuracy at the moment, but before that, I think the limit was 78 or 79. So we are actually using signatures now, I think, to do real world things. A little bit more than we were. Thank you.
Thank you very much. Thank you very much, Felicia. Thank you for we end on a positive note, a practical note. Are there any questions? No? So, I promised coffee in the beginning. So coffee is not being delivered. No, hi. So I hope the coffee is being parked outside. I hope. But in any case, if it is, then we'll enjoy it. If it's not, we'll live without it.